Hello everybody, this is Coach Meinmauer for AP PreCalculus. We are here doing section 2.12, logarithmic function manipulation. This is a lot of review from Algebra 2. There's very little new stuff coming here from AP PreCalc, but let's go ahead and do it. Let's talk about all the properties of logs, and let's go ahead and manipulate these properties. So the first thing we're going to do here is going to rewrite each log. Erase that. Rewrite each logarithmic expression in equivalent form using the product property. The product property is above. That's you're multiplying two arguments inside of a log function. You actually add them and can separate them as separate logs. Make sure the base is consistent for both of those when you write it. And then the division one means we're subtracting. Okay, so for the first thing that we see here is log base 2 of 4 and log base 2 of 8. Since we're adding that, what we can do here is we can write this as log. Okay, so base 2 of 4 times 8, which is just log base 2 of 32. Can simplify that in case you don't know. That would be equal to 2 times 2 times 2 times 2 times 2. That's 32. So that's going to be 5. Okay. Next one, I can combine these, make sure they're the same base. And then this is just going to be 3x. There's nothing else to do for that one. Bottom right here, we're going to have log base 2 of x times y with a z on the bottom. Z's on the bottom because we're subtracting that one. Okay. So now we're going to pull these ones apart for d through f. So this becomes log base 5 of 4 plus log base 5 of x. Okay, so we're just pulling the 4x apart into two separate logs. Bottom one here, log base 7 of 4 minus log base 7 of x. This is one that most people get tripped up on, so let's go ahead and do it. Log base 7 of 4 minus log base 7 of x. Now people are like to say, well, that y is multiplying the x. It sure is, but the y is still in the denominator, so they're going to subtract that one as well. So minus log base 7 of y. So please keep note that these are together both in the denominator. All right. Let's go ahead and talk about, actually, we're going to go down here, and then we'll talk about that graph here in a second. Power property of logs. Okay, this is when you take the power on top and you just multiply it. Oh, I think I'm frozen. Oh, there we go. Hello. I think I'm frozen again. All right. Let's try this again. So when you take the n value and put it, oh boy. You know what? Technology doesn't work when you need it to. You're going to put the n out in front. Okay, so this first one for A, this just becomes 3 times log base of x because we took the power 3, put it in front. For B here, we got two things going on. We're going to separate this as log base 5 of x cubed plus log base 5y squared. And then I'm going to move that 3 in front of this log. Oh, man. Lots of freezing today. Oh, boy. We are on the struggle bus on this video. Plus 2 log base 5 of y. This one right here, I want you to try it out on your own. See how you do. Go ahead and make sure you pause it within 3, 2, 1. Oh, you tried this one on your own? Well, this is what I got. I got log base 3 of x squared minus log base 3 of 9 minus log base 3 of y to the 4th. This all simplifies nicely to 2. Oh boy, this keeps freezing. I know my handwriting is like usually bad, but like I promise I'm being hacked right now. Minus, by the way, log base 3 of 9 is just 2. Oh my gosh, that's not a 2. Minus 4 log. I think this is a practical joke being played on me. Okay. Write each of the logarithmic expressions as an equivalent. Oh, so we're just going backwards for these. Okay, so we're going to throw this 5, put it on top right there. So this is going to be log, no base there, so just base 10, y to the 5th. Oh, this one, we're going to put this 10 on top of this x. We're going to put this 3 arg 10 on the x, 3 on the y, but not only that, I'm going to put these into one log argument. I feel like I'm having an argument with the computer here. It doesn't want to write my stuff. All right, let's come back to this top one right here. So we're going to have a log base 2 of x. We're going to graphic. Okay, this is the graphic representation of log base 2 of x, which is g of x. And we're going to graph 2 separate things here for using that pair function of log base 2. So we're going to get g of x and compare that with h of x. So here we go. By the way, the underscore is next to the 0 if you hit shift. Might be mansplaining or teach-splaining to you young kids how to do that. This is the parent function. Okay. Now, what happens where we have g of x, which is going to be log base 2 of 8x. So the 8x is all together in the argument. This is a horizontal dilation, so we're kind of squeezing everything here in the middle. So we're multiplying this red, everything by 1/8. That's why this value comes in right there by 1/8. This value there comes in. So you can see right here, it's a value of 4 coming all the way in right here to 1/4. Okay, but how does that compare to my h of x, which is now going to be a vertical translation? It is log, it's actually 3 plus log base 2 of x. You can see right there, that green, I'll undo red, that green and blue are exactly the same. So there's blue, there's green. Blue, green. Blue, don't get a seizure, green. All right, so you can see how they're overlapping each other right there. They're the same thing. So for logs, the little special property here is a vertical translation is going to be the same thing as a horizontal dilation if it's the same consistent number. So those two right there are going to work out for us because of our log properties. All right, moving on. Oh, let's go back to Desmos here. Oh, let's just show this now. Okay, so all right, look at this guy. Not green anymore. Okay, so this is log x squared. And this is going to be 2 log base 2 of x. Let's go this color. If you notice, the green one just overlaps the blue one just on the one side. The reason that it does not overlap on the other is blue here, since we're doing an x squared, it gives us, it unlimits our domain. Unlimit, is that even a word? What it does here is it takes our limitation of logs always need to be positive. The arguments need to be. And well, since we're squaring it, every single negative argument becomes positive. So by the way, they do say that just when x is bigger than 0, they do limit. Whoa, me can't type, me old man. There we go. Why can't it do that? Oh my gosh, I think I need to do this. Oh man, me can't type, me old man. There we go. There's blue. Okay, so now when I limit the blue to being just x is being larger than 0, you can see that the blue and the green are the same thing. Okie dokie. Let's talk about Euler's number here. It's not Euler, it's Euler. If we ever see an ln, that's the same thing as a log with base e. So log base e and ln of x are the same thing. We don't say log base e of x, though. That's just weird. It's not logix, it's ln of x. Okay, we use ln of x just because it's much easier when you get into calculus, because again, the rate of change of e to the x is equivalent to its height. So it's just easier to use ln of x. A lot of times for not for just transformations, but for like rates of change. So get familiar with ln of x. So if I wanted to graph ln of x here real quick, you remember I make my x and y chart, but I inverse it. Is that even a verb? Inverse it. So this is 1 over e, this is 1, and this is e. Okay, so 1 over e is like 1/3-ish, go down, 1, 1, 0. Then e is like 2.7-ish. And we're going to go up 1. It's close enough to 2.7. So the graph, oh, come on. There we go. Don't forget you got a vertical asymptote. There you go. Domain and range. Domain, if you look at it, you can see we're going to go from 0 until infinity. If this would work correctly. Range is going to be all real numbers here. Touch every single y value. We increase very slowly, but we do touch every y value. All right, last thing here is a change of base property, which is a cool property, as the kids say. You can change any base you want. It's going to make it into a fraction, and you can see it right there. Make sure that our base is larger than 0 and not 1. So there's a change of base right there. So for example, is the argument becomes a numerator and the base becomes a denominator. So it changes to base 10, which means that we're going to rewrite this as log x on top all over. Hello. Oh my. Bad day at the office. That's what the old people say. That's not what the kids say. Bad day at the office. Okay, so that's going to give me that equivalent right there. So change base of 2 for the next one for B. So to, oh boy, I forgot to pay my electric bill. We're going to get log base 2. Yeah, and my, you know what? I'm going to pay the bills. So all I got to do is just praise, bills get paid. That's a joke. That's not how life works. Okay, log base 2 of 8 on top. Log base 2 of 3 on the bottom. That's equivalent, but we can simplify this. Log base 2 of 8 is, very good class, that is 3. All over log base 2 of 3. Okay, same things. Fun one here. I'll give you log base 5 of x and log base 125 of x to describe the relationship. Well, they're very friendly to each other. Now, I'm going to do a change of base here for g of x. It's easier to change the big number into a smaller number. So g of x is equal to log base 5. So I can make the relationship between these of x all over log base 5 of 124. Come on. There we go. Okay. So now you wrote this as a log base 5 of x. Now what's really nice for this problem, and it's not by coincidence, it's the question maker made this work, the bottom simplifies for us into a 3. So I can really rewrite g of x as 1/3 log base 5 of x. And that is a vertical dilation. That's not how I write dilation. It's supposed to be an L, by the way. By a factor 1/3. Okay, and that's going to wrap up this video, and hopefully my next one works out a little bit better here with my stylus and the power here. Do not forget to like and subscribe.